There are many features, many parts to consider in buying a truck. Some are big features, some small, and some make more difference than others. One that makes an important difference in the performance of your Freightliner truck is a Cummins engine with optimized aftercooling. Optimized aftercooling is a major technological advance in the engine intake air system, designed to further improve fuel economy and to increase engine life in Cummins' new L10 and Big Cam 4 engines. To better understand optimized aftercooling and how it works, let's first look at the evolution of air intake systems, beginning with turbocharging. In the 1950s, Cummins pioneered the use of turbocharged diesel engines to pressurize the intake air so that more air can be packed into the cylinders for improved combustion. However, pressurizing air heats it up, which makes the air less dense and reduces the amount of oxygen. As you know, combustion requires oxygen, and cooler, denser air contains more oxygen than warmer, thinner air. Optimum combustion in an engine is achieved when the intake air temperature is in the range of 100 to 140 degrees. Turbocharged air, however, can reach temperatures as high as 250 degrees, far above the ideal range. To overcome this problem, an aftercooler was added. An aftercooler is simply a small air cooler through which the intake air passes as it moves from the turbocharger to the engine cylinders. The aftercooler uses the engine coolant to help cool the hot turbocharged air down closer to the ideal range, resulting in better combustion and therefore better fuel economy. But the effectiveness of this aftercooler is limited because by the time it receives the coolant has already passed through the engine. As the coolant passes through the engine, of course, it picks up heat from the hot cylinders. This limits the aftercooler's ability to cool the intake air. For example, an aftercooler using coolant that has passed through the engine is only capable of dropping 250 degree Fahrenheit turbocharged air down to 190 degrees Fahrenheit, far above the ideal temperature range of 100 to 140 degrees. To give the aftercooler more capability to lower intake air temperature, Cummins designed optimized aftercooling. Optimized aftercooling is the result of 4 major changes to the engine. These changes were made to the coolant flow, radiator, aftercooler, and thermostat. Let's look at the change that was made to the coolant flow first. Before optimized aftercooling, traditional Cummins engines received the coolant that had already circulated through the engine. Now, with optimized aftercooling, the aftercooler receives the coldest coolant immediately after it comes out of the radiator. This may seem like a small change, but consider the impact that it has on intake air temperature. Remember, an aftercooler using coolant that has already circulated through the engine, picking up heat from the hot cylinders, is only capable of dropping 250 degree turbocharged air down to 190 degrees. In comparison, the aftercooler in optimized aftercooling, which uses the coldest coolant right out of the bottom of the radiator, is capable of dropping the same 250 degree turbocharged air down to 120 degrees, 70 degrees colder than traditional aftercooling systems. This is well within the range for optimum combustion and peak fuel efficiency. Now let's look at the changes made to the radiator. Before optimized aftercooling, radiators were a single-pass design. Coolant entered one side of the radiator and made only one pass before flowing back to the engine. In optimized aftercooling, radiators are a multi-pass design, which increases the distance the coolant travels in the radiator. In addition, with optimized aftercooling, the flow of the coolant through the radiator is much slower than through a conventional radiator, about 85% slower. In a conventional radiator, coolant flows through at a rate of 120 gallons per minute. In an optimized aftercooling radiator, coolant flows through at only 20 gallons per minute. This means the coolant is in the radiator longer, and the longer the coolant is in the radiator, the colder it gets. Finally, to further promote cooling, turbulated tubes are used instead of conventional tubes. Turbulated tubes increase water turbulence, which further increases cooling. The combination of all these changes, multi-pass design, a much slower rate of flow, and turbulated tubes, means that the radiators used with optimized aftercooling are simply far more effective in lowering the coolant temperature as it passes through the radiator. To get an idea of how much more effective, consider this fact. With the single-pass radiator used in traditional systems, the coolant typically enters the radiator at 180 degrees and exits at 170 degrees, a drop of only 10 degrees as the coolant passes through the radiator. With the multi-pass design of optimized aftercooling, the coolant enters the radiator at the same 180 degrees, but exits at 120 degrees, a drop of 60 degrees. By then channeling the 120-degree coolant from the bottom of the radiator directly to the aftercooler, the result is maximum cooling of the intake air for maximum fuel economy and engine life. The third major difference in optimized aftercooling is in the aftercooler itself. It is a two-pass design and has more fins to get more efficient use of the coolant and do a better job of cooling the air. The final change in optimized aftercooling is in the thermostat. It monitors the temperature of the coolant and balances the coolant flow to maintain the coolant temperature at optimum levels. Coolant flow changes according to coolant temperature. At startup, when the engine is cold and coolant temperature is below 175 degrees Fahrenheit, the thermostat causes all the coolant to flow through the engine and directly to the aftercooler, bypassing the radiator. Because the coolant is picking up heat from the hot cylinders and then flowing directly to the aftercooler warms up quickly and helps to heat the intake air. This gets the intake air temperature up quicker to the 100 to 140 degree Fahrenheit range for optimum combustion. In other words, at startup, the aftercooler is doing just the opposite of its normal job of cooling intake air. This warming of intake air is a big bonus you get with optimized aftercooling in your Freightliner truck. Without the use of an add-on heater, engine intake air is preheated to get the engine to optimum operating temperatures faster in colder weather. When the truck is put under load and the coolant temperature reaches its normal operating range, 175 to 185 degrees Fahrenheit, the thermostat precisely balances the flow between the aftercooler and the radiator to maintain this temperature. The aftercooler is now cooling the air, not heating it. When the coolant temperature goes above 185 degrees Fahrenheit, for example, when your truck is climbing a steep grade on a hot day, all the coolant flows through the radiator for maximum cooling. So, whether the coolant temperature is in the cold, normal, or hot range, the optimized aftercooled Cummins engine in your Freightliner truck is giving you better fuel economy and longer engine life. All these changes in the coolant flow, aftercooler, thermostat, and radiator add up to the big advantages of optimized aftercooling. Better fuel economy due to lower intake air temperatures, longer engine life thanks to reduced heat loads, plus faster warm-ups with preheated air. Cummins Engine Company feels there are major benefits that make optimized aftercooling the best choice for your Freightliner truck. Other engine manufacturers, however, have chosen an alternate method of cooling the intake air. This alternate system is normally referred to as air-to-air cooling. With air-to-air systems, no aftercooler is required. Instead, intake air is passed through an air cooler, which is mounted in front of the radiator. The air-to-air system is capable of dropping the turbocharged air down to the optimum temperature of 100 to 140 degrees Fahrenheit when the outside air temperature is between 70 and 110 degrees Fahrenheit. However, when the outside air temperature falls below 70 degrees Fahrenheit, an air-to-air system without some means of bypassing the air cooler will continue to cool the intake air, which means the air is being overcooled. Intake air that is too cool overcools the engine and leads to inefficient combustion. By contrast, when outside air temperature is between 20 and 90 degrees Fahrenheit, incidentally 60 degrees is the average temperature in this country, optimized aftercooling can provide intake air in the ideal range, between 100 and 140 degrees Fahrenheit. As we discussed earlier, optimized aftercooling also has the ability to heat the intake air in cold weather, at startup, and during prolonged idling. Air-to-air systems cannot without the use of an add-on heat source. Now, compare the serviceability of the two systems. Shown here is an air-to-air system in a Mack truck. As you can see, with air-to-air aftercooling, both an air cooler and radiator are required, and large air pipes must be used. With optimized aftercooling, only a radiator is used, and the radiator hoses are smaller. This results in a more compact installation, better access for service, and an air intake system less subject to leaks and dirt, leading to higher reliability. Optimized aftercooling, a technological advancement from Cummins that makes an important difference in the operation of your Freightliner truck. In the L10 engines, optimized aftercooling has provided improved performance in both the PowerTorque L10 270 and PowerTorque L10 240. It's also responsible for the development of two new L10 engines at a higher horsepower, the L10 300 and Formula L10 300, an increase of 30 horsepower in the L10 engine family's horsepower range. And in fuel economy, compare the new optimized aftercooled engines with previous models. The PowerTorque L10 240 is 1.8% better than before. The Formula L10 240 is 1% better. And the Formula L10 270 is 2% better. In Big Cam 4 engines, optimized aftercooling results in fuel economy improvements ranging from 0.4% to 3.2%. These figures are based on actual vehicle mission simulations. Improvements in throttle response in the Big Cam 4 are dramatic, with increases ranging from 20 to 72%. Improved throttle response, drivability, fuel economy, engine life. Optimized aftercooling makes an important difference. Choose the optimized after-cooled Cummins engine to match the Freightliner truck that meets your needs exactly.